All right. So the first thing I should mention is I'm assuming that nobody has any questions or issues with the way their exam and quiz were graded. With both of them, the graded item was shared with you. The um, solution key, the answer key with the marks breakdown was also shared with you. So I haven't heard from anybody, so I'm assuming everybody's okay with that. Let's get back to where we were. Let me go ahead and share my screen. Are you able to see the iPad screen? Okay. All right, so if I'm not much mistaken, this is where we were. I think this was the last thing we've done, is we're talking about this change of variable formula involving the law of a random variable, right? Can anybody back me up on that? I'm pretty sure we're in the proof of this theorem right now. Okay, so since it's been, let's see, it's been at least, this is the first, no, this may be the second lecture after the exams, but it's been a long time. We've missed 2 lectures, right? There was a holiday on Friday last week and on Tuesday. So it's quite possible that people have forgotten a little bit. So I will take the liberty of taking 5-10 minutes to do a brief review. I'm hoping that is helpful for you rather than a waste of your time. Okay, so let's just go back a few pages. Okay, so actually, let me just make a few statements. So we've talked about what we mean by a probability space, right? A probability space is a triple omega fp, where omega is the sample space, f is a sigma algebra, and p is a probability measure. We've talked about what we mean by random variables. We've talked about what we mean by expectations of random variables. A lot of this stuff is basically special case of some things you see in measure theory. So we have talked briefly about what we mean by a measure space omega f mu. It is more general than a probability space. We've talked about what it means for a function to be measurable. Then given a set omega with a sigma algebra f and a measure mu, we've talked about how to integrate functions with respect to mu. We first talked about integrating simple functions. Then we talked about integrating arbitrary non-negative measurable functions. And then we extended it to arbitrary real valued functions. One of the things we saw is that for any non-negative measurable function, the integral is always well-defined. It may be infinity, but it's well-defined. Then we pointed out that all these things we're saying about integrals actually apply to expectations, because the probability space is a special case of a measure space, and a random variable is simply a special case of a measurable function. So this is how we have defined the integral for an arbitrary non-negative measurable function as a supremum of integrals of simple functions, which it dominates. We have talked about certain important convergence theorem. One of the key ones is the so-called monotone convergence theorem. We have stated it here as a resultant real analysis. So I have omega f mu, which is a measure space, may not be a probability space. Suppose I have a sequence fn going from 1 to infinity, which is a sequence of non-negative measurable functions, which is increasing. So fj is less than or equal to fj plus 1, and the functions keep getting bigger. But in that case, the limit is going to exist. It is going to be same as supremum. An integral of limit is limit of the integrals. That's your monotone convergence theorem. We've seen certain properties of integrals like additivity. Then what we did is we translated this stuff into probability. There's nothing clever going on here. We basically just sat with our dictionary and said, this term means this, that term means that. Right, so in probability, a simple function is a simple random variable. What you're calling an integral in real analysis, you're calling an expectation in probability. So everything we said for integrals carries over into probability directly with just a few changes of names. We saw various properties about integration. Another important result was Fatou's lemma. This said if you have a sequence of non-negative measurable functions, then integral of lower limit is less than or equal to lower limit of integrals. Then what did we do? Again, I'm just kind of going over a few things. I know I'm not going over everything. I don't think we can go over everything. I'm just hoping that seeing many of these things will, rekindle various memories you've had about doing this stuff. Then we talked about how you integrate real valued functions, which may not just be non-negative. So we said, suppose omega f mu is a fixed measure space. Suppose I have f taking omega to r, which is measurable. I start by decomposing it into positive and negative parts. The integral of the positive part always makes sense. It could be infinity, but it makes sense. The integral of the negative part always makes sense. It could be infinity, but it makes sense. If at least one of these is finite, then integral f is defined to be the difference of these two. If both these guys are finite, you say f is integrable. Okay, then what did we do? We translated this into probability. Remember, integrals in analysis, integral with respect to a probability measure is just expectation and probability. So we translated this stuff into probability. It's just the language is a little different. Then we talked about the family of all integrable functions being a real vector space and the integral being a linear function along it. We saw this nice proposition which told us 2-3 different ways of saying the same thing. It said, suppose f and g are integrable, then the statement S1, the statement S2, and the statement S3 are exactly the same. Statement S1 is a statement that integrating f over a set A and integrating g over the same set A gives you the same result for every measurable set. That statement S1 is true if and only if integral absolute value of f minus g is 0, which is true if and only if f equals g mu almost everywhere. Then what did we do? Then we looked at this important thing. This was dominated convergence theorem. I'm sure you saw it also in the measure theory class. I know many of you are in that class. Basically, the question we are asking is, suppose I have a sequence fn and it converges pointwise to f. Suppose each fn is integrable. Can I conclude that f is integrable? And further, can I conclude that integral of f is the limit of the integral of fn? In other words, I'm asking the question, is it that the integral of the limit is the limit of the integrals? The dominated convergence theorem gives you a sufficient condition for that. It says, suppose all the fn's are dominated by a single g, okay, which is integrable, then yes, you can draw all those conclusions. We did that. Again, we translated this stuff into probability. Okay, and this was where we did stuff which was a little new, so to speak. So we basically were going to define this new object called the law or the distribution of a random variable. So let's remind ourselves what's going on. Now I have omega fp, which is a probability space. I have x mapping omega to r, which is a random variable. Another way to say that is x is simply fb of r measurable. Now we said that we can talk about a random variable taking values. Okay, so when you want to talk about measurability, you do not need topological structure. You do not need algebraic structure. All you need is a set in sigma algebras. As long as you have a set in sigma algebras, you can talk about measurability. So if I want to talk about a measurable function x defined on omega, I can take its range to be any set S so long as S has a sigma algebra on it. So suppose I have S, which is a set, non-empty of course, and script S is a sigma algebra. I can talk about what it means for a function x taking omega to S to be a random variable. It just means that the function x is measurable. That's it. Anyway, then in this whole business, we define an important quantity associated with the random variable, which is called the law of the random variable or the distribution of the random variable. Let's see what that is. So suppose I have, so this blob right here is my set omega. This egg right here is my set S. X is a function from omega to S. Okay. X, omega has on it the sigma algebra F. S has on it the sigma algebra script S. So now what I have is I have X taking omega to S, which is a random variable. Okay, so X taking omega to S is measurable. So now what do? Suppose somebody gives me a set A in script S. So somebody has given me a set in S, which is measurable. Now what I can do is I can look at X inverse A. What is X inverse A? X inverse A is the set of all points in omega such that when I apply X to it, I will land up in A. So given a set A and S, we can look at X inverse A. Now, by assumption, A is an S, and by assumption, X is measurable. So X inverse A must be in F. In other words, I can talk about the probability of X inverse A. And now I will define mu of this set A to be the probability of X inverse A. Okay, so now what I've done is, remember that P, let's take a different color. The domain of P is F, right? And F is a sigma algebra on omega. But the domain of mu is script S, which is sigma algebra on S. So P and mu live in different worlds. P is a probability measure on omega, whereas mu ends up being a probability measure on the set where the random variable is taking its values. Okay. So suppose I have A here. So suppose I have A in S. So I have A, which is a subset of S, which is measurable. I look at X inverse A. I define mu of A to be the probability of X inverse A. Then we checked that mu is in fact a probability measure. Okay, and it's called the law of X or the distribution of X. So just to reiterate, the probability measure P lives on the domain of X. This probability measure mu lives on the codomain of X. But a lot of the important information about X is carried by this measure. All right. So we have that here. So this is again a repetition. Omega Fp is a probability space. S script S is a measurable space. X taking omega to S is a random variable. In other words, X is Fs measurable. What I'll do is I'll define a function mu taking script S to 0, 1 as follows. Mu of A is defined to be P of X element of A. Now, what is X element of A? X element of A is shorthand for set of all omega and omega such that X omega is in A. And of course, set of all omega and omega such that X omega in A is simply X inverse A. So mu of A is P of X inverse A. Then mu is a probability measure on S script S. And once again, this is the codomain of the random variable, not the domain. And this is called the distribution or the law of X. Any questions so far? Hopefully it's all reasonably familiar by now, even if you don't remember all the details, hopefully you remember enough to get started. Okay, all right. So we checked that this mu is in fact a probability measure. Okay, that has been done. Where are we now? Okay, so this is just formally stating what expectations are. There's nothing new here. Suppose X is a real valued random variable on omega Fp. The expectation of X, denoted E of X, is defined by E of X is the integral over omega X dp. And of course, this is meaningful if and only if at least one of Ex plus and Ex minus is finite. Okay, so here are some statements that basically just carry over from analysis to probability by just changing the names. Okay, and I'm pretty sure this is where we were. We were doing the proof of this particular proposition, and I think we had the last step left. All right, so let's see what this proposition is saying. So let X be a real valued random variable on omega Fp with log mu. So of course, what this means is that X takes omega to R, and as we've said before, whenever your codomain is the real line or the complex plane, unless stated otherwise, the sigma algebra there is always assumed to be the Borel sigma algebra. We made that comment before. So of course, when I say X is a real valued random variable, that means X is F B of R measurable. Okay, so let X be a real valued random variable on omega Fp with log mu. So I've shown that in this picture here. This egg over here is omega. X takes omega to this real line. And now I have a function H, which takes the real line to the real line. Okay, so let H mapping R to R be Borel measurable. All right. Now I can look at the composition. So X goes from omega to R. Then H goes from R to R. So I can look at the composition H composed with X, which goes from omega to R. So the claim is that this composition h of x is a random variable. Second thing is you can think of part 2 as a change of variable formula. Right, it's telling you that the same quantity can be calculated as an expectation. In other words, an integral with respect to the probability measure, but it can also be calculated as an integral with respect to mu. Okay. All right, so the second thing is saying that expectation h of x equals the integral over r h d mu. By the way, this object and this object, there is absolutely no difference between them. It is just notation. On the left, I have not shown the independent variable. On the right, I have shown the independent variable. So these two things that I've circled are just two different notations for the same thing. So there is zero information content in this. The information content is here, that this equals this. This has some information content. Expectation hx is integral over r h d mu. Okay, whenever either side is well defined. And once again, remember that expectation hx, what's going on, expectation hx, you're taking an integral over omega h of x dp. So the integral is with respect to the probability measure p over the original sample space omega. Whereas here, omega is not involved. H is a function on the real line, and I'm taking the integral of h with respect to a probability measure on the real line. Okay, so we said that these two guys are the same whenever either side is well defined. So we made these notes here. So when I'm looking at expectation h of x, the function is h of x, which takes omega to r. And integral is with respect to p on omega f. Once again, the integral is on the domain. Now in integral h d mu, here function is h taking r to r. So in the first case, the integral was over the domain of the random variable. Here, the integral is over this real line. In other words, the codomain of the random variable. Okay, and mu encodes the probabilistic behavior of x. Okay. All right, so now the way, the first part is trivial. The first part is basically saying that a composition of measurable functions is measurable, you know that. Okay, so the first part is done. The second part, you basically have to show that these two guys are the same, right? So now here you use the standard trick, and you will keep using this trick many times in this course. You say, I want to prove this for every function h, right? Let me start with indicator functions. Then let me prove it for simple functions which are non-negative. Then let me prove it for arbitrary non-negative measurable functions. Then by splitting into positive and negative parts, let me do it for general real functions. So if I'm not much mistaken, we went, so step one here I've done is for the case of the indicator function. Suppose h is indicator a for some a and b of r. We check that this is true, right? Expectation hx is integral over r h d mu. Step two follows easily from step one by linearity. If it's true for an indicator function, showing that it is true for a non-negative simple function is a piece of cake, right? It just follows by linearity. And now, can somebody confirm that this is where we are? I think this is how far we have gotten. Does anybody remember? Anybody was here? Dhiren, do you remember?
Yeah. Sir, we have done with first and second step. Third step, we have not done third step. Third step is remaining.
Okay. Thank you. So we have done first step and second step then?
Yeah,
okay.
Yes. Sir.
Let's just quickly go over it. So step one is, suppose H is the indicator of A for some A and B of R. Now, remember, I want to show that expectation of H of X is the integral over of h d mu. That's what I want to show, right? And remember here, this integral is over the real line, right? And this expectation is an integral over omega. So suppose h is indicator A for some A and B of R. Now, what is expectation of h of x? This is going to be expectation indicator A of x. Now, we went over this indicator A evaluated at x omega takes the same value as indicator x inverse A evaluated at omega. Note that here A is a point in B of R, and here you're plugging in the value of the random variable. Here, this thing is a set in F, and here you're plugging in omega. Anyway, these two guys are the same. We've checked that. So this ends up being expectation indicator x inverse A. And now you say the expectation of an indicator function is just the probability. So this is just P of x inverse A. Now, what is P of x inverse A? It is just mu of A. Why is that? That is just by definition of mu. So this is integral over R indicator A d mu. Why is that? Because measure of a set is just the integral over that set with respect to the measure. It's just the integral of the indicator function of that set. And then integral over R indicator A d mu, this is just integral over R h d mu, because remember h is the indicator function. So that takes care of step 1. Step 2 is quite straightforward. Once you have step 1, it just follows by linearity. So in step 2, suppose h is the sum I going from 1 through n, ai indicator capital AI, where the capital AIs are Borel sets in R for 1 less than equal to I less than equal to n. Again, we will note that indicator AI evaluated at x omega is the indicator of x inverse AI evaluated at omega. Okay, and now you'll say, note that h of x of omega, what is this going to be? This is going to be the sum I going from 1 through n, AI indicator AI x of omega. This is just plugging in x of omega into the definition of h. Now I'll say that indicator AI of x omega is the same as indicator x inverse AI of omega. So now I'll get expectation hx is expectation sum I going from 1 through n, AI indicator x inverse AI of omega. And now what I'll do is I'll interchange the sum and this expectation. So I'll get sum I going from 1 through n, AI probability x inverse AI. Of course, probability x inverse AI is just mu of AI. So I'll get sum I going from 1 through n, AI mu of AI. And then I remember that mu of a set is simply the integral of the indicator function of that set with respect to mu. And so I'll get the integral over R, sum I going from 1 through n, AI indicator AI d mu. But this is just integral h d mu. So yes, even for the case of simple functions, the thing is true. So far, so good. So now we're at step 3. So now, suppose that I have H mapping R to 0 infinity. Now this is the fact we use many, many times, right? If I have a non-negative measurable function, I can always find a sequence of increasing simple functions, which increases to it pointwise. I can always do that. So let phi n, I'm going from 1 to infinity, be a sequence of non-negative simple functions. And remember, simple includes measurable, so no need to say that, which increases to h pointwise. Okay. Now remember here, phi n is the function taking R to 0 infinity. Now, for any real number x, phi n of x increases to h of x. Well, that means if the real number you're looking at is x of omega, then phi n of x omega is going to increase to h of x omega. Right? So since for any real number x, phi n increases to h at that real number, for any x of omega, phi n of x of omega increases to h of x omega. So phi n x of omega increases to h of x omega for every omega. So here what you're saying is, you're saying that the composition phi n composed with x of omega increases to h composed with x of omega. All right, and now you just use the monotone convergence theorem. Maybe I should just erase. But by the way, is it a little difficult to follow if I just go over stuff I've written? Would it help you if I write some in class? Because sometimes when you write, you're forced to slow down a little bit. And generally, I find that when somebody's giving a lecture and they are writing, I find it easier to understand because they cannot write very fast, right? So people can talk fast, they can't write fast. So would it be helpful if I wrote some of the stuff down in here rather than just go over the notes? Any thoughts?
Yes, sir, I think that will be. Yes, sir. Yes, sir. I think that will be better if you write and then seeing
It-
you can write.
Was that it'll be better if what?
Yeah, that will be better if you write there some stuff.
Okay. Okay. All right. Okay, so now let's just write a few things here. All right, so now by step 2, what do we know? We know that expectation of phi n of x equals the integral over r phi n d mu, right? That's what we know by step 2, because in step 2, we've proved the claim for simple functions. Now, by monotone convergence theorem, what do I know? I know that expectation phi n of x converges to expectation h of x. Do you guys agree with that? Also, by monotone convergence theorem, integral of phi n d mu converges to integral h d mu. And so now we're done, right? These two integrals are the same. The left side converges to expectation hx. The right side converges to integral h d mu. So expectation of hx must be equal to integral h d mu. So expectation hx equals the integral over r h d mu. Any questions with that? Dhiren, are you with me?
Yes, sir.
All right, and now you want to do this in general for real valued functions, right? So you know this, what you do, you will just decompose it into positive and negative parts. So suppose h taking r to r is Borel measurable. Right now I can write h as h plus minus h minus. You can always do that. Now I will leave it to you to check this, okay? The positive part of h of x of omega is the positive part of h evaluated at x omega. And the negative part of h of x of omega is the negative part of h evaluated at x omega. Okay. So let's just see this. Suppose I look at the positive part of h of x omega. This is going to be h of x omega if h of x omega is greater than or equal to 0, and 0 if hx omega is less than 0. Meanwhile, the positive part of h evaluated at x omega is going to be h of x omega if h of x omega greater than or equal to 0, and 0 if hx omega less than 0. So these two quantities are in fact the same. Similarly, you can check that these two quantities are also the same. All right, so what you get is you have hx equals h plus x minus h minus x. Now, what do you know? Now remember, h plus x is non-negative measurable. Similarly, h plus is non-negative measurable. So by step 3, you know that expectation h plus x is integral h plus d mu. You also know that expectation h minus x is integral h minus d mu. So this you know from step 3. And so now you know that if these two guys are the same and these two guys are the same, whenever at least one of these quantities is finite, you get the expectation. So hence, whenever at least one, so these two guys are the same, so I'll focus on this. And these two guys are the same, so I'll focus on this. So when either this, or both are finite, the expectation is well defined. So whenever at least one of integral h plus d mu, integral h minus d mu is finite, then we get expectation of hx is expectation of positive part of hx minus negative part of hx. But as we saw, positive part of hx is just positive part of h evaluated at x. So I have e of h plus of x minus e of h minus of x. But by step 3, we saw that this guy was integral h plus d mu. We saw this guy was integral h minus d mu. And again, by assumption, at least one of these two is finite. So this difference is meaningful and you get integral h d mu. Any questions with what we've done? All right, so now I want to just go over a bit of terminology. Some of this you have already seen before. So we have talked about moments of a random variable. I'm just restating it. Remember now that we know how to do everything using measure theory. We can take expectations of random variables which may not have a density, which may not have a probability mass function. So suppose x is a real valued random variable on omega fp. If I have k, which is a natural number, then expectation x to the k is called the kth moment of x. You already know this. If I take expectation absolute value of x to the k, that's called the kth absolute moment of x. You know why it's called that. Because I'm taking absolute values before taking the expectation. Suppose ex and ex squared are finite, then the variance of x is defined by variance of x is expectation of square of x minus ex. One of the things we've done is we've seen that existence of higher moments implies existence of lower moments. So if ex squared is finite, then ex is going to be finite. So variance of x is ex squared minus square of ex. We've already done this. Then we said that the variance has the units which are square of the units of x. So if you want a measure of the fluctuations in the same units, you should take the standard deviation, which is the square root of the variance, where standard deviation of x is the square root of variance of x. Okay, so this is again old, right? So suppose if the law mu of a real valued random variable x on omega fp can be expressed, okay. So earlier we had defined continuous random variables, right? That was a calculus-based definition that you could explain to somebody who has never seen measure theory before. But now we've seen some measure theory. And so now you may say, okay, what does density or probability density function mean in the measure theoretical language? Well, it means the same thing, but just to be clear, here's what we're saying. Suppose I have x, which is a real valued random variable on omega fp, and suppose the law mu of x can be expressed in the form mu of minus infinity x equals integral minus infinity to x ft dt, where f taking r to 0 infinity is measurable, then you'll say that x is a continuous random variable and you'll say that x possesses the density f. So when you see this phrase, x possesses the density f, you should think, okay, that is saying that x is a continuous random variable with PDF f. Another way of saying that is if I look at the law, what is this saying? So this is saying that mu of minus infinity small x, which by the way is just the probability that x is in minus infinity small x, right? Which this equality is just true by definition of what the law is, which is p of x less than or equal to small x. This equality is true by just writing the same thing in two different ways, right? To say that x falls in this interval is the same as saying x is less than or equal to small x. P of x less than or equal to small x, remember this is just the CDF of x, a CDF of x at small x. And this we're saying is integral minus infinity to x ft dt. Okay, so this here when we're talking about x having a density, this matches exactly with what we had earlier. Any questions? All right, so here is a fact. So suppose I have x, which is a real valued random variable with density f. Okay. So what does that mean? That means for any real number small x, the probability x less than or equal to small x can be obtained by taking an integral from minus infinity to small x of this function f of t dt. Now you may say, okay, here I'm talking about the situation where x falls in minus infinity x. This is a very particular type of set, right? This is an interval, right? It's infinite on the left, but it's basically an interval. So now you may ask the question, is it true that the probability of x falling in an arbitrary Borel set is the integral over that Borel set of the density? And the answer is yes. So it turns out that for any A in B of R, so for any Borel set, probability that x falls in A is the integral over A f dm. Now here you could get away with calculus, right? Because you're taking an integral over an interval and hopefully this function f of t is given to you. But here, if A is an arbitrary Borel set, then you may not be able to get away with just doing calculus. You may have to use stuff from measure theory to do it. Okay, so I'm going to put this problem on the tutorial because this problem basically just connects what we did using calculus and what we're now doing using measure theory. So let X be a real valued random variable defined on omega fp with law mu. Let H mapping R to R be Borel measurable. Here is the claim. The claim is that if X possesses a density small f, show that expectation of h of x is integral over R, h of x, f of x dx. Okay, whenever either side is well defined. So just to be clear, what is new and what is not new here? We already know that this is true. Okay. Look at the thing I'm underlining. This we've already done. We already know that expectation h of capital X is integral over R h d mu. We already know that the underlined thing is true whenever either side is finite. So all that is left to do is to show that this guy equals this guy. Any questions with what I'm saying? Right, so I have X, which is a real valued random variable on omega fp with law mu. Suppose H takes the real line to the real line and it is Borel measurable. Now suppose X possesses a density small f. So what does that mean? That means the probability that X less than or equal to some real number is just the integral from minus infinity to that real number of the density. We want to show that expectation of h of x is the integral over R, h of x, f of x dx. Okay, whenever either side is well defined. And I'm claiming that part of this is already done. You already know that expectation of h of x is the integral over R h d mu, whenever either side is well defined. So all that remains to do is to show that this integral equals this integral. Okay, can anybody tell me one difference between these two integrals? How are these two integrals different?
So d mu is replaced by f of x dx.
Okay, yeah. Okay. So here you have d mu, here it's replaced by fx dx. What is another way of saying that? What is the integrand? Oh, yeah, go on.
Change of variables, sir.
Change of variables. Okay, let's go another way to say that. What is the integrand here? What is the function you're integrating? H, right? H is the integrand. What is the integrand over here?
hx fx.
Hx fx. What is the measure here? Mu. The measure here is Lebesgue measure. So that's how they're different, right? So this is an integral with respect to mu. And the integrand is just h. This will make sense for any random variable, whether it's discrete, continuous, whatever. If the random variable happens to be continuous and has PDF small f, then this integral of h with respect to the measure mu can be written as the integral of h times f with respect to Lebesgue measure. And of course, integrals with respect to Lebesgue measure, when a specific form is given, that's basically doing calculus. Okay, so I just wanted to mention that that's what happens when you have a continuous random variable. Why do I have this on multiple pages? Okay. Okay, so this is page 108. And this is page 109, which is exactly the same thing. So page 109 can go to the trash. All right. So density is probability density function. All right. So now I want to next talk about independence, right? So let me do a bit of scratch work. I think that may be helpful. Actually, let me not do that. Let me add a page before. Change template, want it blank. Okay, So the next thing I want to talk about is independence. Right now, you all have an intuitive idea of independence, right? Suppose I have two events. I will say that these two events are independent if knowing whether or not one has occurred does not affect the likelihood of the other one occurring, right? So if I have two events A and B, I will say that they are independent if knowing that A has occurred or not occurred does not affect the likelihood of whether B has occurred or not occurred. All right. Similarly, you have this intuition about random variables. If I have random variables X and Y, you'll say that they're independent if knowing what value X has taken is absolutely no use in knowing what value Y has taken. Okay. So now when we're doing this here using measure theory, we will first talk about independence of sigma algebras. Then we will talk about independence of random variables. So in undergraduate probability, the first thing you do is you talk about the independence of events. So let me just make a note of that. So undergrad probability, what you do is you say that you start with this: events A, B are independent if probability of A, B equals PA, PB. And just in case you have forgotten this, here's just a quick reminder that when no set operation is indicated, it is understood to be intersection. Okay. So AB is an intersection. So in undergraduate probability, this is what you would have. Events A and B are independent if P of AB is PA times PB. And then you would say that random variables X and Y are independent if for any sets A, B in R, we have probability that X is in A and Y is in B is probability that X is in A times probability that Y is in B. Right, and of course, at that time, we would have just said for any sets A and B, and now we know that we can't do any sets. The sets actually have to be measurable. Okay. Now, what we'll do here. So we'll first define independence of sigma algebra. So we'll first talk about what it means for two sigma algebras to be independent. So rather than starting with the definition of independence in terms of events, we'll start in terms of sigma algebras. Of course, then I need to tell you how that is connected to this old definition. Then we'll talk about independence of random variables. Okay, and somewhere along the way, I need to convince you that whatever you knew earlier still holds. Okay. So let's see. So suppose I have omega FP, which is a probability space. Right? And suppose G1, G2 are sub-sigma algebras of F. Right, so I'm saying two things here. First of all, I'm saying that, so I'm saying two things here. So I'm saying that G1 is a subset of F. G2 is also a subset of F. And I'm saying that G1 and G2 are also sigma algebras, right? So I'm saying two things here. I'm saying first, that G1 and G2 are sigma algebras, and second, that they are sub-sigma algebras of F. In other words, G1 is sitting inside F, G2 is sitting inside F. All right. So say that G1, G2 are independent if for any A1 in G1, A2 in G2, we have probability of, anyone want to guess? A1 intersect A2 is probability A1 times probability of A2. All right, so that's what we mean by two sigma algebras are independent, right? So if I have sigma algebras G1 and G2, I will say that they're independent if whenever I take any set A1 from the first sigma algebra and I take any set A2 from the second sigma algebra, then the probability of A1 intersect A2 is probability A1 times probability of A2. That's what it means for two sigma algebras to be independent. Okay, now at this point, you may wonder, what about this old definition where we talked about two events A and B being independent, right? So what does that mean? Let A, B be events. A, B are said to be independent if the sigma algebras G1 equals A complement omega empty set and G2 equals B complement omega empty set are independent. All right. So what I'm saying is that now you could say that two events are independent. By the way, would you agree that this is the smallest sigma algebra containing A? And remember, a sigma algebra always has to have omega. That's not negotiable. It always has to have the empty set. That is not negotiable. If it needs to have A, then it needs to have A complement. That is not negotiable. As soon as you put these four things in, you can check it's a sigma algebra. This is the smallest sigma algebra which contains A. Similarly, if I'm taking a sigma algebra containing B, omega has to be there, non-negotiable. Empty set has to be there, non-negotiable for any sigma algebra. If I put B inside, then B complement has to be there. You can check that this thing is a sigma algebra. So anyway, I'll say that A and B are independent if these two sigma algebras are independent. Okay, any questions so far? All right, so now we need to talk about what we mean by independence in general. Okay, so let's erase this density. Okay, let's get to this. Okay, so before I do that, let me do the following. Suppose I take G1, G2, dot, 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 up to G10, okay? Basically, I will say that these sigma algebras are independent if whenever I take any two of them, or I take any three of them, or I take any four of them, or I take any five of them. And in the first case, I take any two sets, and or in the second case, I take any three sets. Third case, I take any four sets. Fifth case, I take any five sets. Probability of the intersection is the product of probabilities. So that's what we're saying here. Right. So suppose omega fp is a probability space. And now suppose I have an infinite collection of sigma algebras. It doesn't have to be a finite collection. So for n greater than or equal to 1, let Gn subset of f be a sigma algebra. Another way of saying this is, of course, Gn is a sub-sigma algebra of f. Now note I have an infinite sequence of sigma algebras here. So I will say that the collection G1, G2, dot, dot, dot of sub-sigma algebras of f is independent if for any natural number n, for any distinct numbers I1, I2 up to In, which are natural numbers, and for any Gi1 in script Gi1, Gi2 in script Gi2, dot, dot, dot up to Gin in script Gin, you have probability of the intersection is the product of the probabilities. Okay, so what is going on here? N tells you how many sigma algebras you're looking at. If n is 4, that means you're looking at 4 sigma algebras. These guys tell you which sigma algebra you're looking at. So suppose n is 4, and these guys, you have I1, I2, I3, I4, and let's say they are 1, 3, 5, and 7. That means you're looking at G1, G3, G5, and G7. Then from each of those sigma algebras, you're picking an arbitrary set. So if n is 4, and these guys are 1, 3, 5, 7, then from G1, G3, G5, G7, you're picking some set G1, G3, G5, G7. Anyway, what independence is saying is take any, suppose for any natural number n, suppose for any I1 through In natural numbers which are distinct, and any set Gij in the sigma algebra script Gij, you have probability of the intersection is the product of the probabilities, then you will say that these sigma algebras are independent. Does that make sense? So basically independence is saying, take any two of the sigma algebras. From each of those sigma algebras, pick any set you like. Probability of the intersection should be product of the probabilities. Now take any 3 sigma algebras you like. From each of those sigma algebras, take any set you like. Probability of the intersection has to be product of probabilities, dot, 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 dot. Take any 16 sigma algebras you like. From each of those sigma algebras, take any set you like. Probability of the intersection of those 16 sets should be the product of the probabilities. And this has to hold for every natural number, every sigma algebras you pick, and so on. Okay, any questions with that? I don't know if I can explain that any better than that. So that's what I mean by a family of sigma algebras being independent. Can somebody give me another way to say this? Using the term subfamily. The family G1, G2, G3, and so on are independent if, I guess if every subfamily is independent, right? I think that's what you'll end up having. Anyway, but this is the definition of independence. And again, note that we have stated definition in terms of sigma algebras. And now we want to talk about independent random variables, but some preliminaries first. Once again, let me sneak in a page here and I'll scribble a little bit on that page. Okay. So now again, I have omega fp, right? And suppose I have random variables, x taking omega to r, and I have random variables y taking omega to r. Now remember, at this point, I only know what it means for sigma algebras to be independent. And now I want to talk about what does it mean for random variables to be independent. So somehow I have to relate these random variables to sigma algebras and then say that the random variables are independent if such and such sigma algebras are independent. Okay, so now this is related to the sigma algebra generated by a set. So I have omega fp, and I have x taking omega to r. Now I ask you a question. What is the smallest sigma algebra? What is smallest sigma algebra on omega with respect to which x is measurable? What would you say? What should be there at a bare minimum in the sigma algebra? So omega has a sigma algebra f. Let's not worry about how small or big f is. I have x taking omega to r. And now I'm saying if at a minimum I want x to be measurable, then what is the smallest sigma algebra f I can take here? Well, if x has to be measurable, then for every a, x inverse a has to be measurable. What is the smallest sigma algebra? Let's give this a name. Let me call this gx. So at a minimum, for every A in BFR, X inverse A should be in GX, right? If GX does not satisfy this property, then X is not going to be measurable. Measurability means inverse image of measurable sets are measurable. So if I ask the question, what is the smallest sigma algebra on omega with respect to which X is measurable, you will say, what is the bare minimum you need? And the bare minimum is that for every Borel set A, X inverse A should be measurable. So at the very least, GX should include all X inverse A. So GX should certainly include the set of all X inverse A, where A is in BFR. Okay. Another way to say this is, now, by the way, when you have one random variable, turns out that GX actually is equal to the set of all X inverse A in BFR. Okay, but what you should do in general is, if you want the smallest sigma algebra with respect to which X is measurable, you should take all these guys and look at the smallest sigma algebra generated by them. In other words, you should look at the intersection of all sigma algebras containing this guy. We have talked about sigma algebras generated by families, right? Remember, we talked about the Borel sets are generated by families E1, E2, E3, E4, dot, 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 up to E8. We have done that. Okay, similarly, you asked a similar question. So what is the smallest sigma algebra on Y, on omega with respect to which Y is measurable? Now, at the very least, so at minimum, GY should contain Y inverse of B for all B in BFR. Okay, and it turns out that in this case, you also have equality. Any questions so far? Now I ask you another question. Now I'm asking this question. What is the smallest sigma algebra on omega with respect to which both X and Y are measurable? So what should be there at a bare minimum? What should be there at a bare minimum? Rishikesh, what should be there at a bare minimum? Vikas, what should be there at a bare minimum?
Sir, X inverse A intersection Y inverse B.
It's right. X inverse A has to be there. Y inverse B has to be there.
Yes.
So again, let me call this G. So you must have G should definitely contain every set of the type X inverse A. It should also contain every set of the type Y inverse B, where A is any Borel set and B is any Borel set. Okay, so at a minimum, this much has to be there. But now, if you have two random variables, this thing may not be a sigma algebra. So let me again choose a different color. This thing this will be a sigma algebra, right? Remember, this is only one random variable. I'll leave this to you to check. Similarly, this guy will be a sigma algebra. I'll leave it again for you to check. And the reason is that you're talking about only one random variable. This guy may not be a sigma algebra. Okay, but whatever the answer to the question is here, the smaller sigma algebra, it must contain these guys. So in other words, if the sigma algebra of interest must contain all of these sets, then I should take G to be the sigma algebra generated by this family. And remember, the sigma algebra generated by a family is the intersection of all sigma algebras containing that family. Any questions so far? Okay, so now let's just write everything out nicely on the next page. Okay, so what you're seeing here is a repetition. I'm hoping the repetition also helps a little bit. All right, let omega fp be a probability space, and let X be a map taking omega to R. Look at the family E, which is the collection of all X inverse B, where B is a Borel set. We had this on the previous slide. We had just called it GX. Same thing. Check that E is a sigma algebra on omega. Okay, this is a do-it-yourself. Check that E is a sigma algebra on omega. On the previous page, we had called E as GX. Now, X is a random variable. In other words, X is measurable if and only if E is a subset of F. Why is that? Well, X is a random variable if and only if the inverse image of every measurable set is measurable. That means if and only if every X inverse B belongs to F, which means the whole family of X inverse B is a subfamily of F. E is the smallest sigma algebra on omega with respect to which X is measurable, and we'll write this. Okay, so this is the notation we'll use. E equals sigma of X. You have seen this before, right? When we talked about sigma algebras, families of sets which generate the Borel sets. Any questions so far? There's just a repetition of what was there in the previous slide, only the names have been changed, that's all. Now let's ask the following question. Suppose I have X and Y taking omega to R. And now I'm asking the question, what is the smallest sigma algebra on omega with respect to which both of them are measurable? Now, what is your first guess? Very least, X inverse A, Y inverse B have to be measurable for any A and B. Without that, it's not going to work. So you may say, okay, my first guess maybe take E hat to be the family X inverse A, Y inverse B, where A and B are Borel sets. This is not quite correct because E hat may not be a sigma algebra. So you should modify E hat a little bit. So the correct modified guess is the following. Smallest sigma algebra on omega with respect to which X, Y are measurable is, this is the notation I'm doing, sigma of X, Y. This is sigma of E hat. This is the sigma algebra generated by X inverse A, Y inverse B, where A, B are in B of R. This is the smallest sigma algebra on omega, which contains all X inverse A, Y inverse B for Borel sets A and B. Another way to say that is, this is the intersection of all sigma algebras on R which contain the family E hat. Okay, so this is the intersection of all sigma algebras on R. I'm sorry. Can somebody tell there's a mistake here? What is the mistake? There's a typo on what I've written. What's the mistake? Is this a sigma algebra on the real line? No, it's a sigma algebra on omega. Okay, so there's the intersection of all sigma algebras on omega which contain the family E hat. All right, so now I'm just making a formal definition. Okay, let me actually go back a little bit. Suppose I had three random variables, right? X1, X2, X3. Then what should I do? I should take x1 inverse of b1, x2 inverse of b2, x3 inverse of b3, where each bi is a Borel set, 1 less than or equal to I less than or equal to 3. I should look at this family. This by itself may not be a sigma algebra. I should look at the sigma algebra generated by that family. That will be the smallest sigma algebra with respect to which x1, x2, x3 are measurable. That will be called the sigma algebra generated by x1, x2, x3. But instead of just having 3, you can have infinitely many. And it doesn't even have to be countably infinitely many. You can have uncountably infinitely many, as we'll see on the next page. Okay. So suppose omega is a set. Okay. Now capital I is some index set. Okay, it could be finite, it could be countably infinite, it could be uncountably infinite, whatever. So omega is a set, capital I is an index set. And for each alpha and I have x alpha, which is a function taking omega to the real line. Okay, so omega is a set. The family x alpha, alpha and I is an index collection of mappings from omega to R. Now I'm defining a new quantity. So the quantity I'm defining is the sigma algebra generated by this family. So the sigma algebra generated by the family x alpha, alpha and I, which is denoted by sigma of x alpha, alpha and I, is defined by sigma of x alpha, alpha and I is the sigma algebra is the sigma algebra generated by x alpha inverse of b for every Borel set b and for every alpha and I. Is this clear? I'm hoping that having done it for 2 and 3 random variables will make it clearer what you need to do here. Right? You have this family x alpha, alpha and I. You take every alpha and I. You take every Borel set b. You look at x alpha inverse of b. You throw all these sets together. And then you look at the smallest sigma algebra which contains that family. Okay, so let me repeat that. Here I have, let me highlight this. The thing highlighted in green is a family of sets. How have I got this family? I have taken every alpha and I have taken every Borel set B. I have taken x alpha inverse of B. I've thrown it into this family. Once I'm done looking at all possible B and all possible alphas, the resulting family that I get in green, that is not the sigma algebra generated by x alpha, but the sigma algebra generated by this green family is the sigma algebra of interest. Does that make sense? And this guy, so this is the family. This is the family you get by taking every alpha, every Borel set B, looking at x alpha inverse of B, and including that set in the family. Once you're done with this, this may not be a sigma algebra. If there's only one random variable, it will be a sigma algebra, but in general, it will not. So now I'm looking at the sigma algebra generated by this family, and that is by definition the sigma algebra generated by the family x alpha, alpha and I. And what is this? This is the smallest sigma algebra on omega with respect to which each x alpha is measurable. Right, and now of course you have seen this sort of thing for 2 and 3 random variables. Okay, so now the question is, once again, okay, so let's do the following, just to convince ourselves we understand this. So what is sigma of x1? Well, sigma of x1 is going to be sigma of x1 inverse of A, when A is in BFR. Right now, you may say that this sigma is unnecessary, and you are correct. When there's one random variable, it is unnecessary, but I'll just write it. Okay, and in general, so sigma of xn, what is sigma of xn? This is just sigma of xn inverse of A, when A is a Borel set. Okay, so now the thing is, we've talked about independence of sigma algebra, and the question that may come to your mind is, what is independence of random variables? Here's the answer to that question. So a collection xn, n greater than or equal to 1, of real valued random variables on omega fp is said to be independent if the associate family of sigma algebras is independent. Now remember, the sigma algebra generated by xn is sigma of xn. So now we're saying that if I have a collection xn n greater than or equal to 1 of real valued random variables on omega fp, then this family is independent if the associated family of sigma algebras, namely sigma of xn n greater than or equal to 1, is independent. Okay, and what is sigma of xn? Sigma of xn is sigma of xn inverse of b for every Borel set b. And since you're talking about one random variable, this is just, you can drop this sigma, no problem. So this is just xn inverse of b for every Borel set b. Any questions? Okay, so that's what we mean by independence of random variables. Here is another fact. This just follows from what we have just said. So here is a fact. Suppose I have x1, x2 dot dot dot, which is a collection of real valued random variables on omega fp. Then my claim is that x1, x2, and so on are independent if and only if for any n greater than or equal to 1, any distinct indices I1 through In, and any Borel sets Bi1 through Bin, the probability of the intersection j going from 1 through n, xij in Bij is product j going from 1 through n, p of xij in Bij. So basically this is saying that take any natural number n, such as 3. Pick any 3 random variables. Let's say x4, x7, x9. Pick any 3 Borel sets, call them B4, B7, B9. Then the probability of intersection x4 and B4, x7 and B7, x9 and B9 is the product of the probabilities. That's what you're saying. Now it's saying take n equals 4 and take any 4 numbers. So let's say I take 4, 8, 12, and 16. Then take any Borel sets in B4, B8, B12, B16. Then the probability that x4 is in B4 and x5 is in B5, x4 is in B4 and x8 is in B8 and x12 is in B12 and x16 is in B16 is the product of the probabilities. So this is exactly like what you had earlier. So take any number n of random variables. Okay, so then I1, so let's say you decided to take 5 random variables. Now which 5 you should take? You're going to take these 5, xi1, xi2, xi3, xi4, xi5. For each of them, you have to take a Borel set, bi1, bi2, bi3, bi4, bi5. Then you're going to look at the probability that xi1 is in bi1 and xi2 is in bi2 dot 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 up to xi5 is in bi5. A probability of this intersection to be the product of probabilities. That's what you mean by independence. Okay, any questions with this? All right, now this thing is something we have kind of said earlier. We said it for the case of 2 random variables, but this is true in general. So again, our basic definition of independence is in terms of sigma algebras. So when you want to talk about independent random variables, you look at the associated sigma algebras. When you want to talk about independence of events, again, you look at the associated sigma algebras. Okay, so events A1, A2 dot 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 are called independent if the corresponding sigma algebras E1, E2 dot 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 are independent. What is En? En is the smallest sigma algebra containing An. Now, any sigma algebra always has to have the empty set and nothing. And if it has An, it has to have An complement. Any questions? So I think we may have seen something like this when we did the calculus-based probability, but this is true here also. So independence means multiply. Okay. With probabilities, you're going to say probability of the intersection is the product of the probabilities. But it turns out that something similar is true with expectations also, except with expectations, you won't be talking about intersections, but expectation of a product of 2 independent random variables is the product of the expectations. Okay, so let's look at this proposition. So let x and y be independent random variables defined on the same probability space omega fp. Okay. Basically, I want to say that if x and y are independent, then exy is EX, EY. Then I want to say that E of x to the 4 y squared is E x to the 4 E y squared. This is all because of independence. In general, I want to say that expectation of fx gy is expectation of fx expectation of gy. So I'm saying that if independence is there, then this will be true, this will be true, this will be true. Okay. Any questions with what we're stating here? I'm not asking about the proof yet, but any questions with the statement? All right, so let's just go over this. Basically, we're saying that if I have two independent random variables and I take any function of each of them and I take the product and I take the expectation, then expectation of product is product of expectations. That's basically what I'm saying. Okay, so let x, y be independent random variables defined on the same probability space omega fp. Suppose f, g are functions taking r to r, and suppose they're Borel measurable. And suppose that expectation absolute value of f of x is less than infinity, expectation absolute value of g of y is less than infinity. So basically, I want to say that expectation of f of x times g of y is expectation f of x times expectation g of y, but remember, you want to be sure, you need to be sure that various integrals are finite. So you need some technical conditions which ensure that integrals are finite, and this is your technical condition. Any questions with what this is saying? Now the proof will follow a very similar thing. You will say, suppose f and g are simple, or maybe you want to start earlier, you might say, suppose f and g are indicator functions. Prove the result. Then say, suppose f and g are simple functions which are non-negative. Prove the result. Then suppose f and g are non-negative measurable. Come up with an increasing sequence of simple functions. Prove the result. Suppose f and g may not be non-negative. Then decompose into positive and negative parts and prove the result. So that is the basic plan. Any questions with that plan? That's what we're going to execute. As I've said before, this is an argument you will see many times. Okay, so proof step one. So suppose f and g are simple. I'm not going to do the step where they are indicators. Let's just start with simple. Suppose f and g are simple. Okay, so suppose f of x is the sum I going from 1 through n, ai indicator ai of x, and g of x is sum j going from 1 through n, bj indicator bj of x. So let these guys be the standard representations. So now if I look at f of capital X of omega, which I just write as f of x, this is going to be the sum I going from 1 through n, ai indicator ai of x omega. Now we have used this fact earlier. Indicator ai evaluated at x omega is the same as indicator x inverse ai evaluated at omega. Similarly, g of y is going to be sum j going from 1 through m, bj indicator bj of y omega. And again, indicator bj of y omega is indicator y inverse bj evaluated at omega. So what do you get? You get that f of x is the sum I going from 1 through n, ai indicator x inverse ai of omega, and g of y of omega is sum j going from 1 through n, bj indicator y inverse bj of omega. Any questions so far? All right. So now what will I do? I'll look at expectation of f of x times g of y. That this is going to be expectation of what is f of x? It's sum I going from 1 through n, ai indicator x inverse ai. G of y, that summation j going from 1 through m, bj indicator y inverse bj. Now I'm taking a product of these two sums, so I'll get expectation double sum I going from 1 through m, j going from 1 through n, ai bj indicator x inverse ai intersect y inverse bj. Now remember, this is a finite sum, right? And we're talking of everything non-negative, so I can interchange the expectation and summation. So I'll get sum I going from 1 through n, and sum j going from 1 through m, ai bj probability x inverse ai intersect y inverse bj. Now what is probability x inverse ai intersect y inverse bj? That's probability that X belongs to AI and Y belongs to BJ. Now the probability that X belongs to AI and Y belongs to BJ by independence is probability X belongs to AI and multiplied by probability Y belongs to BJ. So this is sum I going from 1 through n, sum j going from 1 through m, AI, bj, p of x in AI multiplied by p of y in bj. And now I will write this double sum as a product of two single sums. So I'll write this as a product of sum I going from 1 through n, AI, p of x inverse AI, multiplied by sum j going from 1 through m, bj, p of y inverse bj. And then I look at this and I'll realize that, hey, this is just the expectation sum I going from 1 through n, AI indicator x inverse AI, multiplied by expectation sum j going from 1 through n, bj indicator y inverse bj. And then you realize that this guy is just expectation f of x. This guy is just expectation g of y. And so you've proved the claim. So you've now proved it for simple functions when f and g are simple. Next time we'll go over the usual argument. We'll then prove it for arbitrary non-negative functions. Then we'll prove it for real valued functions by decomposing into positive and negative parts. All right, any questions?